Alright guys, the last thing I want to kind of discuss before we work on the homework problem is going past the equivalence point. So we added 25 milliliters of the sodium hydroxide to the 25 milliliters of the acetic acid, and that got us to the equivalence point. Well, what happens if we add more sodium hydroxide, which is kind of what you guys saw in the titration lab today, is adding more of the sodium hydroxide to the hydrochloric acid and kind of seeing what happens. So let's say as we were doing this titration, we added a total of, not 25, sorry, that would be the equivalence point. We added 50 milliliters of NaOH. So just like every step we've done so far, we're going to do a reset button. So we're going to pretend like none of the acetic acid and sodium hydroxide have reacted. So we have our reaction with hydroxide, sodium hydroxide, going to form H2O and our acetate ion. And just like last time, we're going to do our moles. So 1 times 0.02 gives us 0.025 moles. And then 1 times 0.05 is going to give us 0.050 moles. Of course, we don't care about water. 0 acetate ions. So here, notice what happens. Instead of our hydroxide being the limiting reactant, our acid becomes our limiting reactant. So all of this is now going to react, which means 0.025 moles of this is going to be reacting. Should be a minus, sorry about that, and then plus 0.025 moles. So from here, we have no acid left. We still have 0.025 moles of our sodium hydroxide left, and we have 0.025 moles of our acetate ions. So the question comes down, we have 2 species in solution, both of which are base. We have the conjugate base, the acetate ion, and we have sodium hydroxide, because remember this is sodium hydroxide. Well, which one controls the pH of the solution? Well, the answer is like it always has been, the stronger one. Sodium hydroxide is a strong base, whereas our conjugate base is a very weak base. So the sodium hydroxide is controlling our pH, so he's the one we're going to use. We're actually going to pretty well ignore the acetate ion and work with the sodium hydroxide only. So if sodium hydroxide is a strong base, how do we find the pH of a strong base? Well, we need the molarity. Well, if we look at what happened here, we started out with 25 milliliters, we added 50 milliliters, which means we have 75 milliliters. So to find molarity, moles over liters, we are dividing our 0.025 moles by 0.075 liters. Okay? And that's going to give us a molarity of 0.33 molar. And remember, sodium hydroxide being a strong base dissociates completely, which means we can take the concentration of sodium hydroxide and assume that's the concentration of the hydroxide. So we also have 0.33 molar hydroxide. So find pH. We're going to take the negative log of that concentration. But pay attention. We're now taking the negative log of the hydroxide ion concentration, which actually means we're finding POH, not pH. Okay? So our POH is going to be 0.48. Okay, how do we calculate pH? We subtract that from 14. Our pH is going to be 14 minus 0.48, which gives us 13.52. Okay, so that's the final step of a titration. You're not typically asked this question, but it does come up, so I do want you to be able to kind of see how it works. This is going past the equivalence point. So let's look at the homework problem you guys had for last night. Okay, the homework problem was a 2003 AP question, came from the AP exam, and it's dealing with this weird substance called aniline. And they were nice enough to tell us it was a weak base, and they were nice enough to give us the reaction. So the first thing we're asked to do is just to simply write the Kb expression. Well, hopefully we can do that at this point in time. Kb is going to be products over reactants. So we have our products, which are C6H5NH3 plus multiplied by hydroxide all over C6H5NH2. Okay, and that's very commonly the first question in most equilibrium questions on the AP exam. It's also typically only worth 1 point, but it is still 1 point. That can still be the difference between a 4 or 5. Okay, so let's move on to part B, and I'm going to kind of move these around a little bit so that we actually can see what's going on. There we go. Okay, now part B, we're told we have a sample of aniline is dissolved in water to produce 25 milliliters of a 0.1 molar solution. We're then told the pH of that solution is 8.82. Calculate the equilibrium constant, Kb, for this reaction. Well, I'm going to pull this reaction down and we're going to work with it. Okay, hopefully that gives us a little bit more room to work with. So if we are trying to figure out Kb, and we know Kb is the concentration of the conjugate acid times the hydroxide ion divided by the concentration of the original base, all of these values are at equilibrium. That means we need to get those concentration values at equilibrium. Well, how do we do that? We do that with our typical ice table. Okay, so we know this is 0.10 molar to begin with. Don't care about water. 0, 0. So we're shifting towards the products. Okay, and we end it with 0.10 minus x, and x. And at this point in time, for a lot of the problems we worked with, we would just use our Kb value, plug it into our expression, and solve for x. However, we don't have that option this time because we have two unknowns. We have our x value, that's our unknown, and we have our Kb value, that's unknown. That's where this other piece of information is important. We're told the pH is 8.82. Well, what does that mean? Well, let's look at the equation. pH is the negative log of the hydrogen ion concentration. So if we know pH, we can calculate the hydrogen ion concentration. Now the problem is we don't have hydrogen in this reaction, so that really doesn't help us all that much. But we do know that pH and POH are related, and POH is equal to the negative log of the hydroxide ion concentration, which means if we could figure out what POH is, we could figure out the hydroxide ion concentration, and that concentration just happens to be X. So let's go through and do that. Okay, well, pH we know is 8.82. So 14 minus 8.82 is going to give us, okay, that's going to give us a POH of 5.18. From there, we plug that into our POH calculation. So POH equals negative log of hydroxide. So 5.18 equals the negative log of the hydroxide ion concentration. Well, we bring the negative over first. Okay. Then we take these statements, both of them, to get rid of the log and make it exponential. So what we end up with is 10 raised to the negative 5.18 is going to give us the concentration of our hydroxide ion. Okay. So when we do that math, what we end up with is our hydroxide ion concentration is equal to 6.61, there we go, times 10 to the negative 6 molar. Now what we can do is plug this value back into our ice table for x and solve for our equilibrium expression. Okay, so, sorry, not sure why it's spazzing like that. We end up with Kb is going to be equal to 6.61x times 6.61, also x, so x times x, these guys right here, divided by 0.10 minus 6.61 times 10 to the negative 6, 0.1 minus x. Okay, and when we go through and do that math, what we get is a Kb value of 4.37 times 10 to the negative 10th. So that takes care of B. A little bit of work on that one, and a little bit of problem solving. So just kind of remember there's a couple different ways this problem can be asked. You could be given pH. You could also be given percent dissociation, which we've seen before in class. And you could also be given the concentrations and be asked to, and the Kb or Ka, and asked to find the equilibrium concentrations or your pH. So a couple different ways this question can be asked. I'm going to stop here for right now because I'm running out of time on this video, and I will do part C, D, and E on the next video. Thanks, guys.